Hey guys, welcome back to chapter 16. So what we're going to talk about now is we're just going to explore acid-base strength. So later on in the chapter, we will define the strong acids. There's not many things in chemistry I have you just memorize. This is probably going to be one of them, is memorizing strong acids. And then also strong bases. But what we're going to do now is we're just going to explore the strength of some acids, just to kind of get an idea of where we come up with something being a strong or a weak acid. So how do we know? What are some of the things that are involved in this? Okay. So how does the structure of a molecule affect acidity? So we're going to look at two different types of acids and talk about their strength based on the structure of the molecule. So the first ones that we're going to talk about are binary acids. So a binary acids would be something that has a hydrogen and it's attached to one other element. So HCl, HF, HBr, that sort of thing. Oxyacids are exactly what they sound like. They're going to be acids that contain oxygen. So hydrogens bound to an oxygen bound to another atom. So in oxyacids, we're going to have oxygens that are included in the molecule. Okay. For binary acids, we're going to talk about two different things that affect the strength of the acid. So we're going to talk about bond polarity. So what's the difference in the electronegativity of those atoms? And we're going to talk about bond strength. So how strongly are those two atoms connected to one another? For oxyacids, we're going to talk about the electronegativity of the, we'll call it the other atom involved in this. So like I said, for oxyacids, you're going to have a hydrogen, an oxygen, and then some other atom Y. So we're going to talk about how the electronegativity of that other atom affects the strength. And then we're going to talk about the number of oxygens attached to that guy. So is there one attached? Is there two? Is there three? Is there four oxygens attached? And how does that affect acidity? So first, we're going to talk about binary acids. So again, binary acids are things like HCl versus HF. One of these acids is a strong acid. One of these acids is a weak acid. They look very, very similar in structure. So why is one strong and it completely dissociates? Why is one weak and it only partially dissociates? Okay. So binary acids, we're using this Y just to be the other atom. I don't know why they choose Y here, but they do. So Y is the other atom. So two things that we need to consider. First, we need to consider bond polarity. We need to think about the electronegativity difference between the two atoms. And then we also need to consider the fact that we want the partial positive to be on hydrogen. So again, electronegativity, that's just a chart that is given to you or one that you can look up pretty easily. And we're just going to look at these numbers, look at the difference between hydrogen and whatever atom it's connected to. Okay. So here are three examples of hydrogen bound to another atom. First, let's look at hydrogen and lithium. So the electronegativity for hydrogen is 2.1. The electronegativity for lithium is 1.0. Okay. So if I subtract the electronegativity for these two atoms, it is a polar bond, right? So it's between that 0.5 and 2.0. So it does fall within the polar region. But in this case, hydrogen is the big brother, right? So hydrogen is more electronegative. So he's doing a better job at attracting the electrons to himself. So in this case, we would see the partial negative over big brother and the partial positive over little brother. Well, that's not going to make for an acidic situation, because for an acid, when these do dissociate or when this bond does break, what is the charge on the hydrogen? Yeah, it's got to be a positive charge, right? It's got to lose that electron. So if it's over here hogging electrons and has a partial negative charge, do you think he's going to break away as a positively charged ion? Not likely. Not likely at all. Okay. So when we look at the electronegativity difference, one of the things we have to consider is that the partial positive has to be on hydrogen. Looking at this middle scenario, so again, we're looking at the electronegativity difference. So hydrogen is still 2.1, and the electronegativity for carbon is 2.5. Well, good news here is that carbon is big brother, right? So if carbon were to cause a separation of charge, carbon would be the one that's hogging the electrons. So hydrogen's the little brother. That's the scenario that we want. But when we look at the electronegativity difference here, we see that the electronegativity difference is just 0.4. So this is actually a non-polar bond. Okay, there's no separation of charge. Nobody's hogging the electrons. So if nobody's hogging the electrons, or there isn't a separation of charge, this isn't going to be an acidic compound either, because we don't see that partial positive on hydrogen. It's just sharing equally with carbon. And then here we see HF. So HF is an acidic bond. So the electronegativity for fluorine is 4.0. Electronegativity for hydrogen is 2.1. So when you subtract those two, we get a pretty significant difference at 1.9. Okay. So certainly big brother, little brother, certainly a polar bond. And in this case, we see that fluorine has the partial negative, hydrogen has the partial positive. So we've got a polar bond. We've got hydrogen with the partial positive. So this would be a scenario where this would be an acidic bond. So we do have the possibility for these to dissociate from each other. Okay. So electronegativity facilitates this loss of a hydrogen, and as hydrogen gets lost, it facilitates the fact that it's going to be positively charged. So that's the first thing that we need to look at with bond polarity. Electronegativity difference needs to be large, and the partial positive has to be on hydrogen. The other side of this is bond strength. So in order for this bond to officially break, and for those two to dissociate from one another, we need to look at how strongly those two atoms are holding on to each other. So the strength of the bond will affect how easily or how difficult it is to pull the hydrogen away. So here we see 3 examples of binary acids. So we see HF, HCl, HBr. We see the bond energy here. So bond energy, remember, is the amount of energy that you have to put in to break that bond, to pull those two atoms apart. So HF has the highest bond energy. That's going to be the strongest bond. HBr has the lowest bond energy. That's going to be the weakest of these 3. And remember, if we look at these are all halogens, so moving top to bottom. Fluorine is a smaller atom, so those two can come closer together, which makes the bond stronger. And then the electrons that are being shared are also closer to the nucleus. So they're in the first energy level, where for bromine, they're in the 3rd energy level, so a little further away from the nucleus. So small atoms close to the nucleus makes this a really strong bond. Bigger atoms, so bromine's a bigger atom. Those electrons are a little further away from the nucleus. It makes it a little bit weaker. So although there is a big difference in the electronegativity between hydrogen and fluorine, there's a lot of energy that would have to be that have to go into that to break that bond apart. So hydrofluoric acid is actually, a type of a weak acid. So even though the electronegativity difference is large, it's really hard to pull those two apart. So this would fall into the category of a weak acid. Hydrochloric acid. So hydrochloric acid, if we look at the electronegativity difference between hydrogen and chlorine, so the electronegativity of chlorine is, I have it written down here, 3.2. Electronegativity of hydrogen is 2.1. So if we subtract those, again, it's a pretty significant electronegativity difference. So certainly a polar bond. And then with that bond energy decreasing just a little bit, it's a little bit easier to pull these two atoms apart. So what we see is that hydrochloric acid is going to be a strong acid. So when we put hydrochloric acid into solution, it's going to completely dissociate or completely break apart into all of its ions. Same thing with hydrobromic acid here. So electronegativity difference still gives us a polar bond, and then it's a little bit easier to break those apart. So again, a strong acid. So there's two things at play here. There's this electronegativity difference, and then there's also a bond strength. So it's not just a black and white, yes or no, right or wrong answer. There's a lot of factors. That's one of the things that makes acids so difficult. There's a lot of things going into it. So as we move from left to right, our electronegativity difference increases. As we move top to bottom, our bond strength decreases. So on this chart down here, this HI would be the strongest of the acids with having a high electronegativity difference and a decreased bond strength. And we see water would be on this chart the weakest of the quote unquote acids. So water can behave as an acid, but it also can behave as a base. So certainly we would think about it as an acid in this scenario, but it's going to be a relatively weak acid. Okay. All right, so that was binary acids. So now what we're going to talk about are oxyacids. So oxyacids, remember, have a hydrogen, an oxygen, and then some other atom Y as that central atom. So there's other things that are attached out here. So Y is the central atom. So two things we need to consider here is the electronegativity of Y. So how does the electronegativity of Y affect the strength of this acid? So high electronegativity assists in the polarization of this OH bond here, of this bond right here, okay? So if Y has a higher electronegativity, so here's chlorine, it's got an electronegativity of 3. What that's going to do is that's going to assist in the separation of charge between this oxygen and this hydrogen, okay? So here we're going to see a partial positive, partial negative, and over here we'll see more partial negative. So we want the electronegativity difference to be greater over here. So those electrons are really drawn away from the hydrogen and towards the center of the atom. So if we draw those electrons towards the center of the atom, that's going to make this hydrogen more susceptible to being removed, which is our definition of an acid. Here we see the electronegativity of Y is a little bit lower. So while these electrons are still being drawn towards the center of the atom, it's not such a strong draw. So there is still a partial positive over here, but it's not quite as strong as this partial positive here. So this hydrogen still has the ability to be cleaved off. It's just not as great of an opportunity. Okay. So a higher electronegativity of Y assists in the polarization. The number of oxygens attached to Y. So as I said, is there one attached over here? Is there two? Is there three? So the more oxygens that are attached, that decreases the electron density of Y, further polarizing that OH bond. So essentially what these other oxygens do over here is they create more of a draw for those electrons. So if there's one oxygen, it's drawn this way. If there's two oxygens, it's drawn in two different directions this way. If there's three oxygens, those electrons are drawn in three different directions, further polarizing this bond right here. So in short, the more oxygens that are attached to Y, the more polarized or separated that bond's going to be, and the stronger the acid's going to be, the more susceptible this will be to be cleaved off. Okay. So here we see just working our way, I guess, down the table. We've got 4 oxygens, 3 oxygens, 1 oxygen attached to that chlorine, and we see strong, weak, to very weak. So again, these oxygens are pulling the electrons away from that hydrogen and out the other side. Okay. So more oxygens, stronger the acid. I hope you guys found this section helpful.